Hi everyone. In this video, I will explain a very good concept of vector algebra, right? This is the video 2 regarding collinear, non-collinear, coplanar, non-coplanar vectors and condition for collinear, non-collinear, coplanar and non-coplanar vectors. There are considerable questions asking in JEE Main. And those questions I will discuss at the end of discussion of these concepts. Okay, so these concepts are so simple, they are not at all difficult. The very basic one is what is meant by collinear vectors. What is meant by collinear vectors? Collinear vectors means they have to move in the same line. They have to move in the same line, right? Okay, so here two vectors are collinear if one is the scalar multiple of the other. If one is the scalar multiple of the other. If a bar is a vector, then 2a bar, 3a bar, half a bar, minus 2a bar, minus 3a bar. These are all collinear vectors. They are either in the same direction or they may be in the opposite direction. Well, so here suppose I can take that this is a point A and this is point B and point C. All right. So they are collinear vectors. Assume this is origin. And assume this is A bar vector. A bar vector. And this is lambda A bar vector. This is equal to B bar vector. So here particularly lambda is negative as the direction is opposite. As the direction is opposite. So remember two vectors are collinear if one is the scalar multiple of the other. There is another condition that if we write two vectors as a xa bar plus yb bar equal to 0 bar, then at least one of x and y must be not equal to 0. Must be not equal to 0. Then only we can write as a bar equal to tb bar or b bar equal to ta bar. Then what is the condition for collinear vectors? What is the condition for non-collinear vectors? I will write the same expression that xa bar plus yb bar equal to 0 bar implies whatever we have multiplied scalars x and y, those all must be zeros. So x equal to y equal to zeros. Then a bar and b bar are non-collinear vectors. Okay, remember this point is very, very important for non-collinear vectors. A bar, x a bar plus y b bar equal to 0 bar implies x equal to y equal to 0. If x is not equal to 0, then you can write a bar equal to, suppose if x not equal to 0, for example, x not equal to 0. Then what we can write? Then we can write that a bar is equal to minus y by x into b bar. Now, which means that a bar, b bar are collinear. A bar comma b bar are collinear. Are collinear. So this is a contradiction statement. This is a contradiction statement. So that's why x must be 0. That's why x must be 0. All right. Okay. So as it is a contradiction, so therefore therefore x equal to y equal to 0. So a bar and b bar are non-collinear vectors, means either they are neither moving in the same direction or in opposite direction. Assume this is a of a bar vector and this is b bar vector. Now if you take any vector in the plane of a bar and b bar, two non-collinear vectors determine a plane. Therefore, if you take any vector in the plane of a bar and b bar, in the plane of a bar and b bar, then we can write that R bar as linear combination of A bar and B bar. That is X A bar plus Y B bar. How do we prove it? Proof is quite simple. You just draw the lines parallel to P and passing through P and parallel to A bar and B bar. So I am drawing a line that parallel to B bar vector. Assume this is M. And I am drawing a line parallel to A bar vector. All right. Assume this is N. So OM is collinear with A bar vector. So you can say that it is some scalar multiple of A bar vector. And here you see ON is scalar multiple of B bar vector. Therefore, there exists some scalar. Therefore, it is YB bar. So now apply vector addition that XA bar plus YB bar is equal to R bar vector. That I wrote here. So any vector in the plane of A bar and B bar, we can write R bar equal to XA bar plus YB bar. For example, you consider rectangular coordinate system. All right, rectangular coordinate system. This is x-axis. This is x-axis. Along x-axis, I cap is the unit vector. Along x-axis, I cap is the unit vector. Along y-axis, I cap is the j cap is the unit vector. So if I take, for example, this is a comma 0, and this is, you can say that ai, and this is 0 comma b, and this is known as bj. Now this vector p of a comma b, that point, now I can write that ai plus bj. So any point in two-dimensional space, we can write as a vector form. Here I and j are the unit vectors, okay? Respectively unit vectors along x and y axis. Now, what is the magnitude of this vector? What is the magnitude of this vector, right? So here OP bar vector is equal to AI plus VJ. You can use the coordinate geometry so that it is easy to find out that magnitude of this vector equal to root over distance between O and point A comma B, that is root over A square plus B square. Now I'm going to explain what is linear combination of vectors. Linear combination of vectors is nothing but you multiply some scalars to the vectors and add them. Multiply some scalars to the vectors and add them. That is known as a linear combination of vectors. Suppose you take A bar and B bar, 2A bar plus 3B bar is a linear combination. 2A bar plus 3B bar plus 4C bar is a linear combination. A bar minus B bar plus C bar is a linear combination. So you just multiply some scalars to the vectors, that is known as a linear combination of vectors. That is sigma xi ai bar. Sigma xi ai bar. For example, I will write that 2a bar plus 3b bar, comma 3a bar minus 2b bar plus 3c bar. These are all linear combination of vectors. Are all linear combination of vectors. Linear combination of vectors. Now, from this linear combination of vectors, we can decide what is meant by linearly independent vectors and what is meant by linearly dependent vectors. If all, whatever scalars we have multiplied, if all are zeros, then the vectors are linearly independent vectors, right? So suppose you take that sigma ai xi bar, sigma xi into ai bar equal to 0 bar, sigma xi into ai bar equal to 0 bar, I equal to 1 to n. So if all scalars are zeros, then the vectors are linearly independent vectors. See here, if all scalars are zeros, then the vectors are linearly independent vectors. If at least one of the scalars which we have multiplied is not zero, say at least one of xi is not zero, then it is called, then the vectors are called linearly independent vectors. Okay. Later on, I link between linearly independent, linearly dependent, and collinear, non-collinear vectors, and coplanar and non-coplanar vectors. So now what is meant by coplanar vectors? So coplanar vectors means either they should lie on the same plane or their supports are parallel to the same plane. Their supports are parallel to the same plane. So for example, I would like to draw a few vectors. All right. So here you see, oh, I'll take some vectors on this plane. Okay, this is one vector, this is another vector, this is another vector, or they may be parallel to the plane. Like this also I can take. These are all coplanar vectors. We can move the vectors. Like assume that this is A bar and this is B bar and this is C bar and this is D bar and this is E bar. These are all coplanar vectors. We can move parallelly onto the plane. Now, what is meant by non-coplanar vectors? If the vectors are not lying on the same plane, then they are known as non-coplanar vectors. They lie on different planes, isn't it? So here, if we take some two vectors on one plane and some two vectors on another plane, like this, or you take one vector, or you take like this. So these vectors are non-coplanar vectors, right? These vectors are non-coplanar vectors. Well, so three non-coplanar vectors divide the space. Three non-coplanar vectors divide the space. These concepts are very important, helpful to J main, J advanced, intermediate, or CBSE, any kind of examination regarding 10+2. Right. So the vectors which are not coplanar are known as non-coplanar vectors. If A bar, B bar, C bar are non-coplanar vectors, if A bar, B bar, C bar are non-coplanar vectors, and if you give any vector in the space, then that can be written as a linear combination of given non-coplanar vectors. This is the linear combination. R bar equal to XA bar plus YB bar plus ZC bar for some scalars XYZ belongs to R. This is a very important concept and very important point. Here I have taken three non-coplanar vectors, not lying on same plane. Well, now you see that if you take any vector in the space, join that, okay? After that, you draw a line parallel to C bar vector passing through P. All right. This is parallel. Suppose it meets that AOB plane at some point Q. AOB plane at some point Q. Now join O and Q. All right. So you see that now it is very simple. Now we know that Q lies in the plane of A bar B bar. Q lies in the plane of A bar B bar. So therefore, this is nothing but XA bar plus YB bar. All right. Now you see that QP bar is parallel to C bar vector. So therefore, this is ZC bar vector. Now apply vector addition. You will get that R bar is equal to XA bar plus YB bar plus ZC bar. So any vector in the space determined by A bar, B bar, C bar, non-coplanar vector can be written as linear combination of A bar, B bar, C bar. It is very important. Now, if you consider that rectangular coordinate system in three-dimensional space, like a rectangular box. Now you take that x-axis, y-axis, z-axis, right? So along x-axis, you take that xi cap. Along y-axis, you take yj cap at some distance y. And along z-axis, you take zk cap. Now this is the point xyz. Now you see this P1 lies in the plane of xy. So this is nothing but xy 0. So what is this vector? This vector is xi plus yz. Now apply that R bar is equal to xi plus yj. Okay, that is OP1 plus P1P. This is equal to ZK. This is nothing but OP1 bar plus P1P bar vector. Now it is easy to verify that magnitude of R bar vector is magnitude of R bar vector or OP bar vector is equal to, this is equal to root over x square plus y square plus z square. How? How do we know that? Because we know that modulus of OP1 bar, just now I have proved that this is equal to root over x square plus y square, isn't it? Now this is a right angle triangle. So therefore that OP is equal to root over OP1 square plus P1P square. Apply this concept. That's it over. So remember, any point in the space written by A bar, B bar, B bar can be written as XA bar plus YB bar plus ZC bar. If you take coordinate axis, x-axis, y-axis, z-axis, then any vector R bar can be written as xi plus yj plus zk. This is known as a general vector in three-dimensional space. Now I am going to discuss a few more important points to solve the questions. Up to till now, I have explained only concepts, but how to apply those concepts to solve the questions? Here you see. Suppose you consider two vectors. You consider two vectors. A bar is equal to A1I plus B1J plus C1K and B bar equal to A2I plus B2J plus C2K. Be two vectors. A bar, B bar are collinear vectors are parallel if and only if that A1 by A2 is equal to. Means these are the ratio of components of I components is equal to B1 by B2 is equal to C1 by C2. Okay, so I would like to tell you that here what are x, y, z in this vector. In this vector, that xi plus yj plus z. Okay. So this is known as a scalar component, or simply component, scalar component along x-axis, or you can say scalar component of I, Similarly, y is the scalar component of j, and zk is the scalar component of k. Xi is the vector component, yi is the vector component, zk is the vector component along z-axis. So remember that two vectors that A bar and B bar are collinear. Two vectors A bar and B bar are collinear if the ratio of I components and j components and k components are same. So remember, two vectors are collinear is nothing but one is the scalar multiple of the other. So here A bar equal to, you can say TB bar, which means that A1I plus B1J plus C1K equal to some scalar into that B bar vector. You write that BA2I plus TB2J plus TC2K, isn't it? Now we have that these two vectors are equal. So therefore, these are equal. These components are equal. That we get this is equal to something. So remember, two vectors are collinear is nothing but their ratio of I components, scalar components of I, j, and k are equal. Now, how to do when 3 points are given? How to do when 3 points? Suppose A, B, C are collinear. A, B, C are collinear. Nothing but this is A and this is B and this is C. Okay. So you see that AB bar is collinear with the AC bar. They are in the same direction. Then AB bar is parallel to, then AB bar is parallel to AC bar. Then how do we write that? This implies AB bar is equal to lambda into, you can write any scalar. Remember, this is very, very important. Lambda into AC bar vector. Well, now what is meant by coplanar and non-coplanar vectors? Now, one more point I would like to revise that. What is the condition for collinear vectors, non-collinear vectors? If A bar, B bar are non-collinear vectors, right, non-zero and non-collinear vectors, then XA bar plus YB bar equal to 0 bar implies X equal to Y equal 0. Once again, I am repeating. Or PA bar plus QB bar equal to RA bar plus SB bar implies P equal to R. P equal to R. These two are equal and these two are equal. Nothing but scalar components of A bar, scalar components of B bar, both are equal. All right. Now coming to that coplanar and non-coplanar vectors. Let A bar, B bar, C bar be three vectors such that XA bar plus YB bar plus ZC bar equal to 0 bar. Now, what are the conditions on X, Y, Z so that A bar, B bar, C bar coplanar or non-coplanar vectors? Well, so if at least one of X, Y, Z is not zero, then they are said to be coplanar vectors. Is not zero, then they are known as coplanar vectors. Then A bar, B bar, C bar are coplanar vectors. This is important. So coplanar vectors means one vector can be written as linear combination of the other. One vector can be written as linear combination of the other, like R bar equal to XA bar plus YB bar, right? Coplanar vectors. If all X, Y, Z all are 0. If X equal to Y equal to Z equal to 0, remember, this is very, very important. Then A bar, B bar, C bar are non-coplanar vectors. A bar, B bar, C bar are non-coplanar vectors. If at least one of them is not 0, then they are coplanar vectors. Now, how to decide whether the given vectors are coplanar or non-coplanar using determinant method? Okay. Here I will apply that application of matrices, solving of linear equations. So condition for coplanar and non-coplanar vectors. Consider three vectors. A bar is given, B bar is given, C bar is given. Right. Be three vectors such that XA bar plus YB bar plus ZC bar equal to 0 bar. Now, I would like to take that A equal to determinant of A1, B1, C1, that is first vector, scalar components of first vector, first row. Second vector along the second row, third vector along the third row. So A2, B2, C2, A3, B3, C3. These are the three vectors. I wrote only scalar components. The vectors A bar, B bar, C bar are coplanar, or you can say linearly dependent vectors. Coplanar or linearly dependent vectors. If det A equal to 0. So this is a very simple one, very simple. If just determinant equal to 0, then the vectors are coplanar vectors. And the vectors are non-coplanar, or you can say linearly independent vectors. Then det A not equal to 0. There are plenty of questions based on this coplanarity condition. Right? So, I will give you a very subtle proof to this. So you just substitute A bar and B bar and C bar vector in this equation, linear combination. So I have just substituted. Here Ijk are non-coplanar vectors. I, J, K are non-coplanar vectors. So therefore, we have to equate that scalar components equal to 0. We have to equate that scalar components are all zeros. On equating scalar components of uh, I, J, K, we get these three equations. This is the homogeneous system of equations. We can write this in the form of matrix form. Okay, right? Suppose this is the system Bx equal to 0. So homogeneous system will have a trivial solution. Trivial solutions means all variables equal to 0, provided that B is not equal to 0. If, if that B is not equal to 0. Okay. This implies anyway transpose of determinant is same as of without transpose. Det A equal to det A transpose. Det A equal to det A transpose. Right. For trivial solution, sorry, not equal to 0. So if det A not equal to 0, then the system, homogeneous system, will have a trivial solution, that is all variables equal to 0. For non-zero solution, that det B must be not equal to 0 implies that A not equal to 0. So remember that for non-coplanar vectors, determinant must be not equal to 0. For coplanar vectors, determinant must be equal to 0. Implies that A equal to 0. Because the det A equal to det of B transpose equal to det B. Now, what is the condition that 4 points are coplanar? Instead of vectors, sometimes they will give 4 points, right? 4 points. 4 points A of A bar, B of B bar, C of C bar, D of D bar are coplanar, right? So I have taken 4 points in a plane. Now fix one point A and join the other points like this. I have joined. Now join with A and C. Now join with A and D. Right? Okay. So now you see that. Now see AB bar vector, AC bar vector, AD bar vector are all on the same plane. So this implies nothing but AB bar vector, comma, AC bar vector. This is important. Many questions are asked, are there based on this concept. AD bar vector or coplanar or coplanar. So when they are coplanar vectors, so determinant equal to 0. This implies determinant equal to 0 according to above one. And not only that, if they are coplanar, then one vector can be expressed as linear combination of the other vectors. So AB bar equal to sum T into AC bar vector plus some S into AD bar vector. All right. So what is AB bar vector? It is nothing but B bar minus A bar vector. And this is equal to T into C bar vector minus A bar vector. Isn't it? Plus S into, you see that this is D bar vector minus A bar vector. All right. So this, we got that. I will write one equation that is A bar into 1 minus T minus S. 1 minute. 1 minus T minus S. 1 minus T minus S. This is also very, very important point. Plus B bar vector into, okay, this is equal to, all right, B bar minus, this I am bringing this side, minus B bar vector plus TC bar vector plus SD bar vector. This is equal to 0. Right. So if I say that this is XA bar vector plus YB bar vector plus ZC bar vector plus WD bar vector equal to 0 bar. What is sum of all these scalars? X plus Y plus Z plus W equal to. You will get 1. You will get 1. Add all these values. This, okay, and this and this. I hope this is 0. Check it out. 1 minus T minus S minus 1 plus t plus s equal to 0. In the right time, you won't be able to remember this point. If 4 points are coplanar, then xa bar plus yb bar plus zc bar plus wd bar equal to 0 bar implies x plus y plus z is equal to 0. Now, I'm going to solve a few previous JEE mains questions. Okay. First question based on collinear vectors. Okay, read the question clearly. A bar, B bar, C bar be non-zero such that B bar and C bar are non-collinear vectors. So B bar and C bar are non-collinear vectors. If A bar plus 5B bar is collinear with C bar. Okay, so A bar plus 5B bar is collinear with C bar. So therefore, this is equal to some lambda into C bar. Collinear vectors means one vector is the scalar multiple of the other. Like I plus j, 2i plus 2j. These are the collinear vectors. Now, B bar plus 6C bar is collinear with A bar. B bar plus 6C bar is collinear with A bar. So you take some mu A bar. Now, which are non-collinear? B bar, C bar are non-collinear. B bar, C bar are non-collinear vectors. So let us try to write the equation in terms of only B bar and C bar. So eliminate A bar vector. Okay. Eliminate A bar. So that you will get an equation in terms of only B bar and C bar. Eliminate A bar. Well, how to eliminate that? From this equation, what is A bar vector? Lambda C bar minus 5B bar. Right? So therefore, B bar plus 6C bar equal to mu into lambda C bar, okay, minus 5B bar. Now, what are B bar, C bar? They are non-collinear vectors. So you just equate these scalar components. So here B bar scalar component is 1. That's equal to lambda into mu. And 6 is equal to minus 5 mu. That's it. Got it? Okay. So we got it. All right. So therefore, this implies lambda mu is equal to minus 6 by 5 and that lambda is equal to minus 5 by 6. All right. So if A bar plus lambda alpha B bar plus beta C bar equal 0, then what is alpha plus beta? This is the question. Oh, I did a very blunder mistake equating this here. Okay, this has gone wrong. Now you see that we have to equate this. All right. So this implies that minus 5 mu equal to 1, right? And mu equal to minus 1 by 5. And lambda into mu is equal to 6 implies what is lambda value? Lambda value equal to minus 30. All right. Okay. So substitute here. A bar plus 5B bar equal to lambda C bar. That's equal to minus 30 C bar. Implies A bar plus 5B bar plus 30 C bar equal to 0. Bar, 0 bar. So implies alpha plus beta equal to 35. There are some 2-3 more questions based on the same concept. You please try to practice them. Moving to next question. This is also regarding only collinearity of two vectors. Here alpha bar a vector is given. This is an alpha bar vector. This is a beta bar vector. and A bar, B bar are non-collinear vectors. The value of lambda for which the vector alpha bar and beta bar are collinear vectors right? So here you see that alpha bar and beta bar are collinear vectors. So here alpha bar comma beta bar are collinear, isn't it? So collinear is nothing but one vector is the scalar multiple of the other. So alpha bar is equal to some t into beta bar. T into beta bar. Now what is alpha bar? Substitute alpha bar. Lambda minus 2 into A bar plus B bar equal to substitute beta bar t into 4 lambda minus 2 into A bar plus 3t B bar vector. Now, what are A bar, B bar? A bar, B bar are a non-collinear vectors. So, equate their scalar components, right? These two are equal and these two are equal, right? So, this implies, first I'll equate that 1 equal to 3t, right? And lambda minus 2 equal to t into 4 lambda minus 2. This implies t equal to we got 1 by 3, isn't it? So therefore, now we can get the value of lambda, right? So lambda minus 2 equal to 1 by 3 into 4 lambda minus 2. I hope you can do these calculations. Right. This is 3 lambda minus 6 equal to 4 lambda minus 2. So implies lambda is equal to, you can say minus 4. So let us do a few more questions based on this collinearity. These are the vectors are collinear. Now 3 points are collinear vectors. 3 points are collinear. Read the question, you see, this is the assume point A, this is assume point B, and assume this is point C. Now A, B, C are collinear. So therefore, A, B, C are collinear is nothing but AB bar is parallel to AC bar vector. AB bar is parallel to AC bar vector. So what is AB bar vector? You just subtract A bar vector from B. Okay, right? Subtract A from B. You will get that 6 minus alpha into I, okay, 11 minus 10, that is plus j, and 11 minus 13 plus 2k is parallel to AC bar vector. 9 by 2 minus alpha, 9 by 2 minus alpha into I, okay, plus beta minus 10 j, okay, plus that is some 21k. So now these vectors are parallel. So therefore, you just take the ratio of I, J, K components. So therefore, we got that 6 minus alpha by 9 by 2 minus alpha equal to 1 by beta minus 10 equal to 2 by 21. Now it is easy. You just need to equate two ratios so that you will get the required values. Suppose, for example, equating these two, you will get that 21 after doing cross multiplication. Okay, it is 2 beta minus 20 implies. So what is 2 beta value? That's is equal to 41. All right. Okay. Now taking the first two, equating first and last. equating first and last. Do the cross multiplication. I have done here. This we got 19 alpha equal to 117. So what is 19 alpha minus 6 beta whole square? This you will get, this is equal to 117 minus 123. Okay. This is into 3. Right. 123 whole square. That's equal to 8 square. 6 square. That's equal to 36. All right. Now, based on the coplanarity of vectors, let the position vectors of A, B, C, D are given. We want to find out all values of lambda for which A, B, C, D are coplanar vectors. So A, B, C, D are coplanar vectors means nothing but AB bar vector, right? AC bar vector, right? And AD bar vector. These are all coplanar vectors, right? So when they are coplanar vectors, nothing but determinant of these vectors equal to 0. So you write that determinant of first AB bar vector. So AB bar vector nothing but subtract A from B. You see I minus 5I is nothing but minus 4. And 2j minus 5j is nothing but minus 3. Be careful. You will definitely commit mistakes. So 3 minus 2 lambda. Even I 3 minus 2 lambda. Next, AC bar vector. Subtract C, right? Subtract A from C. Right. This is equal to minus 2i minus 5i. This is minus 7. And lambda minus 5. Isn't it? Next, 4 minus 2 lambda. 4 minus 2 lambda. Last one, AD bar vector. Minus 1 minus 5, that is minus 6. And 5 minus 5, 0. And it is 6 minus 2 lambda. This determinant equal to 0. First row, first vector, second row, second vector, third row, third vector. Now it is our task to expand the determinant, right? So you please try to expand the determinant as fast as you can do. Better you expand the determinant about the third row because 1, 0 is there. Okay, I'll do that expansion now. I'm expanding the determinant about the third row minus 6 into, okay, this is minus 12 minus plus 6, okay, cofactor of this one. And anyway, 0 you don't write, plus 6 minus lambda, 6 minus 2 lambda into, I'm not explaining that how to expand the determinant. I hope that you know this 6 minus 2 lambda into minus 4 lambda plus 20 minus 21 equal to 0. So on simplification, you will get that after simplification, lambda square minus 5 lambda plus 6 equal to 0. We get that lambda is equal to 2 or 3. Therefore, that set S contains only two elements, that is 2, 3. Further, question is not yet finished. They are asking what is lambda plus 2 whole square, where lambda belongs to S. Substitute one value of lambda. You will get that 2 plus 2 whole square plus 3 plus 2 whole square. That's equal to 4 plus 9. That's equal to 13. Oh, sorry, 4 plus 25. This is 16 plus 25. 16 plus 25, that's equal to 41. And one more question is left. Here you see, this is also based on coplanarity. Here U1, U2, U3 are coplanar vectors. Okay. U1 bar, U2 bar, and U3 bar are coplanar vectors. Isn't it? So therefore, determinant equal to 0. What is the determinant? 1, 1, A first vector, second vector 1, B 1, and third vector C 1, 1 equal to 0. So 1 into this is B minus 1 into 1 minus C and plus A into 1 minus BC equal to 0. I hope that you will get that this is A plus B plus C is equal to ABC. Okay, here ABC plus 1. Now you see that V1 bar vector, V2 bar vector, V3 bar vector are coplanar. So this coplanarity of vectors is nothing but application of determinants. Application of determinants. If you are so good at determinants, then it is easy to solve those kind of questions. So again, we have to apply the determinant for V1, V2, V3. So for V1 vector, first V1 vector is A plus B, C, C, and V2 bar vector is A, this is B plus C, and this is A, and next B, B, and C plus A equal to 0. So we have to that expand this determinant and use this condition, then you will get the answer. Okay, I'll expand this determinant. Here we need to apply some row transformations that you add first row, second row, and subtract from the third row, right? So adding that first two rows and subtracting from third row, that 2a plus b, subtract from b, then you will get minus 2a. Here that b plus 2c, subtract from b, you will get minus 2c. And add a and c, subtract from this. Now expand it. Minus 2a into minus 2a about third row, right? About third row, you will get AC minus BC minus C square. Minus of minus plus 2C into, right? A plus B into B plus C minus AC equal to 0. You just have a patience and simplify that. You will get ABC equal to 0. So therefore, A plus B plus C equal to, we got 1. Now what is the answer for 6 into A plus B plus C? That answer is 6. This question is very good based on two-tiered coplanar vector system linked with determinant application. Thank you. Keep watching my channel and enrich your knowledge.